Welcome back. We are going to talk about limits at infinity. And before we give some formal definitions, let's go ahead and look at this graph and answer some questions. The graph y equals f of x is shown. Use limits to describe any vertical asymptotes on the graph of f. Or if there's none, state that there's none. Well, I see a vertical asymptote here at x equals -4, and then I see another one here at x equals 2. And this says use limits to describe. So first we're going to start here. As the function approaches -4 from the left, we're getting bigger and bigger. So we're going to infinity. So the limit as x approaches -4 from the left, this is going to go to positive infinity. Now we'll do the same thing, except for approaching -4 from the right. And as we get closer and closer to -4, we're seeing that the limit as x approaches -4 from the right is going to be negative infinity. And let's see what's going on at x equals 2. As we go towards 2 from the left, we're going to negative infinity. So the limit as x approaches 2 from the left, this is going to negative infinity. Then we can look at what's happening as we approach 2 from the right. We're going to positive infinity. So the limit of x as it approaches 2 from the right, this is going to be positive infinity. If you look at each of these, the x is approaching a numeric value and the limit is going towards infinity or negative infinity. And these are the things that qualify something as a vertical asymptote. We'll go ahead and formalize that definition in just a moment. Now, this next problem says use the limits to describe any horizontal asymptotes. Horizontal asymptotes are really looking at end behavior. It looks to me like we have a horizontal asymptote right at y equals 1. We'll first look at this graph as we approach negative infinity. So the limit as x approaches negative infinity is going to equal 1. Let's look at the other side. As x approaches infinity, we're going to keep at that value of 1. So the limit as x approaches infinity, that's going to equal 1. All right, let's define a vertical asymptote. That is going to be for a line x equals a. It's a vertical asymptote if any of the following are true. The limit as x approaches a from the left of f of x equals negative infinity, or the limit as x approaches a from the right is negative infinity, or the limit x approaches a from the left is positive infinity, or the limit as x approaches a from the right is positive infinity. These are a general form of everything we did in part A. All right, now let's talk about a horizontal asymptote. A line y equals b is a horizontal asymptote if the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x is b. So we've seen how these definitions apply graphically. We saw that in that first example. But what happens if we don't have a graph? What happens if we have a rational function, which, if you recall from the last video, would be h of x equals f of x over g of x, or if we have an exponential function or a polynomial function. So let's talk about what we do for rational functions, and then we'll have an example of an exponential function, and then as those other functions pop up, we'll talk about them. What we're going to do is we're going to look at the degree or the power. So if the degree of the numerator is greater than the denominator, then the limit as x approaches infinity of f of x is going to be infinity. And that is because f of x grows without bound. Now, if the degree of the numerator is less than the denominator, then the limit as x approaches infinity of f of x is going to be 0. If the degree of the numerator equals the denominator, then the limit as x approaches infinity of f of x is going to equal the ratio of the leading coefficients. Then for other non-rational functions, we just need to remember that if we have a constant over infinity, that is going to be 0. If we have infinity over a constant, this is going to be infinity. Well, let's do some examples. This first one is not a rational function, but we want to find the limit as x goes to infinity of e to the x. Just a reminder, e is a number. It is not a variable. So it is the same thing if I said 7 to the x or 3 to the x. So for this one, we have a number raised to a power, and that power is infinity. Well, this is going to go to infinity. Let's think about it. If I have e squared, we can do that, or e to the 8th, or e to the 10th. The number is just going to keep getting bigger and bigger and bigger. If you ever want to verify this, you can just go ahead and throw out your graphing calculator, and the graph looks something like this, and it'll just keep getting bigger and bigger. All right, let's look at problem 14. And now we're going to use the rules that we had on the previous page. It says to look at the degree. Well, the highest degree in the numerator is 3, and the highest degree in the denominator is 3. This says if the degree of the numerator equals the degree of the denominator, then the limit of f of x is going to equal the ratio of those leading coefficients. What that means is these terms drop out, and we're left with the limit as x approaches infinity of 4x cubed over negative 3x cubed. Those divide out, and I'm left with just negative 4/3. Now, I'm sure you're wondering, why did you drop those out? The reason is because when you think of infinity, think of these very large numbers. A very large number raised to the 3rd power is going to be an even larger number. When we compare that to something like 12 times infinity, that is going to be a much smaller number than something that is infinity cubed. So that means these terms drop off. They won't have a big impact in our overall answer. So then we're left with just comparing those coefficients. Now let's look at the next one. We have the largest degree in the numerator is a 1. We don't write the 1, but it's there. And the largest degree in the denominator is also a 1. So the 3 drops out, and these x's will factor out, so I'm left with 4/7. And you could throw those both in the calculator and you'll see that that is the limit at infinity. And one more thing to add is that when we're looking at the limit as we approach infinity of f of x, or the limit as we approach negative infinity of f of x, what we're really talking about is the end behavior. What is going on at the ends of these graphs? We are also looking for horizontal asymptotes. So now you have opportunity to do some practice problems, and you can watch the next video for the solutions.